Recording. Okay, so today we are talking chapter 8, 1 through 3. Shared state concurrency. Yeah, this is pretty okay, I would say. This section of the book is pretty fine. Like I literally had I returned from my trip today and I'm still very tired, but I was not tired enough to not understand this. This is very okay. Um, okay, so what are we doing? We want to introduce concurrency into the stateful model, and the first thing that it does is things are hard.
Yeah, it turns out when you have
That things are
multiple
hard.
mutable yeah, it turns out when you have mutable things that are being manipulated by multiple people, they can get confused.
Well, not necessarily because of that, but because it's observable non-determinism, and it's the stateful model. Because if you just want concurrency, you can use the other things. You can use the message passing and the declarative concurrency, and that's okay. The problem comes from the interleaving, right? So there is even the math here. How many interleavings are possible in a particular program? So let's consider if we have a bunch of threads and we have a bunch of operations inside each thread. We have the binomial thing to represent how many possible executions considering all the possible interleavings. And things are hard because can you make sure that for all of these execution paths the program is correct and it's going to work? So that's the problem. That's actually the main thing why this is hard. And then, okay, if this is hard, why are we doing that? And I think this is a pretty good point that the book makes about reminding the reader that we already talked about this many times, but I always think it's a good thing to remind people about, okay, why again this is a problem? Why can't we use the other things? And it's because the declarative model is deterministic, and we must introduce an observable non-determinism, and it keeps bringing up the server-client implementation example. So we must, it's not that we would like to, we must do that. So that's why we cannot just keep things simple. Yes?
Yeah, and the book actually makes a really good point here that if you can get away with just using message passing, that's usually simpler. But there are a few things that the message passing model doesn't fit very well. So shared
Yeah.
state is
We're gonna talk more about that.
yeah.
Pretty good, pretty good. Okay, so then we we go in getting around the difficulty. So the programming this is full concurrent model is largely a matter of managing interleavings. You have two ways to do it: message passing between ports and objects. So we saw this in chapter 5. But uh, a port object executes in a single thread. So there's this caveat. And it's going to talk about that usually message passing is associated with multi-agent programming. And then we have atomic actions on shared cell, which is what we're going to be talking about. Uh, so there are advantages and disadvantages. We're going to also talk about that. Then we have the structure of the chapter, which I must say, why is this the last thing? Like, this is so anticlimactic, right? Why? I don't know
Uh,
why they do this, but okay.
I mean, they build up the
Why?
concepts and then they conclude with, okay, here's how here's how the concepts are typically applied nowadays, right? Which is nice. It gives the book some grounding, but yeah, I have to agree, it's anticlimactic.
Yeah, it's very like. Okay, anyway, so then this is written weirdly because it says chapter 4 adds concurrency to the declarative model. This allows to have multiple active entities that evolve independently. The next step is to add both explicit state and concurrency to the declarative model. One way to do this is given chapter 5 by adding ports. This chapter gives an alternative way by adding cells. Yeah, I missed the word both here, so that's why this phrase is okay. It's because we want to add both things at the same time. We already saw explicit state before. in chapter 6.
Yep.
Cool. Okay, now programming concurrency, and then we have the separation here of the models, and it's pretty straightforward. We have like dumb programming, which is like sequential programming. Then we have declarative concurrency, which is well, chapter 4. By the miracle of data flow variables, we can do this. Then we have message passing concurrency, which we saw with port objects and later with active objects. And now we're going to see shared state concurrency, which is this chapter. And funnily enough, we're not going to be talking about all the usual abstractions that are usually associated with shared state concurrency. But to give the book some credit, I consider like mutex, semaphore, just like variations of locking. So it's okay.
Yes, I agree that those omissions are okay because they're like, okay, those are things that are kind of like locks but with different details, right?
Yeah.
One thing that the book doesn't mention, and I think it would be a better book if it did, is atomic lock-free operations like compare and swap and the things you can build on top of that.
No, but it does. That's it. But it only it mentions one, which is exchange.
But exchange is not equivalent to compare and swap
No,
lemmas
it's not. No,
because
it's not the same. But it has the atomicity, which I guess it. Well, I guess would be the core principle you want to be talking about. I was not um, understanding that you want to specifically talk about like shift and.
because like if you use exchange and data flow variables, you are still doing a very lightweight form of locking. And in fact, the book later on it actually defines locking in terms of that.
Yeah,
What
we will
compare and
see that
swap
today.
gives, yeah, locking is basically like pessimistic concurrency, where you say, okay, I'm going to mess around with mutable things concurrently. Let's just take turns so we don't mess each other up, right? It's very like I'll grab the lock, and then if somebody else tries to do this at the same time, they have to wait,
Mhm.
right?
Mhm.
Um, Compare and swap gives you a different style of programming where it's like optimistic concurrency, where it's like, okay, I have two people, they're trying to change the same mutable variable
Mhm.
simultaneously using
Mhm.
concurrency. They'll both proceed without waiting for the other. One of them is gonna win, and the other is gonna have to retry.
Ah, okay. Okay, so that is definitely different than just atomicity for the sake of it. Yeah, I
Yeah.
agree. I agree that it should be talking about that. Okay, then we're gonna talk about. Yeah, this figure is very nice. So it explicitly tells you like how do you divide, like the division between things. Very nice. And then we go to sequential programming. So we have order determining concurrency. This is the declarative concurrency. We have coroutining, which we also saw, and we also saw that with lazy evaluation. Um, yeah, then it talks about declarative concurrency more, about the being like incrementally giving you output. We've seen this before multiple times. I'm not complaining about that, just that we already are okay with that concept. It talks about to see the clarity, the non-determinism must not be observable, but then we have the problem. We have the demand-driven concurrent model, which uses laziness. Oh, that's all that good stuff. Nothing too crazy. Then we have the message passing, chapter 5 and 7, 8. Port objects, active ports, active objects, sorry. Shared state concurrency, which is we're gonna be talking more about now. And then relationship between ports and cells. And then the end of the story, the summary, that they are equivalent in expressiveness, so, because you can implement one in terms of the other, but usually they are associated with particular styles of programming, so you want to keep them separate anyway.
Also, small spoiler, they also have different semantics when we get to distributed programming later in the book.
That makes sense, but that's like spoilers. Um, and then we have other approaches using the stateful concurrent model directly, um, using cells and ports. We have the non-deterministic concurrent model, which is the thing about using the choice operator, like doing the runtime yourself, I guess.
Yeah, we're gonna see a little bit of that when we get to um, relational programming.
Cool. And then here's the guideline. Use the least expressive model available that solves your problem. That's very that sounds very really dumb, like very obvious that you should always do that. Sometimes you want to future-proof yourself because you already know you're gonna have to upgrade in the future, so you may already start with a more powerful model. Just be careful about that. Just don't do like, how
Just
should I
keep it
say?
simple. Yeah, just keep it
Yeah,
simple.
yeah. Keep it as simple as it makes sense, considering a little bit of future-proofing. But you have to do the trade-off math about how much more expensive the future-proofing will be if I do this now in comparison to doing it later. All those things you need to consider. This is a very tricky math. Experience guides you, stuff like that. But essentially, the guideline is use the least amount of power as possible. Like this is the complete opposite of C++, right? You are not gonna give you everything up front. You need to earn it. You need to have an argument to justify. So like constraints. Like we are fan of constraints. We are fan of restricting ourselves on purpose because that gives us more peace when we sleep at night.
Yeah, we want to be the wise sage living in the mountain instead of the mad scientist.
Yeah, that's a pretty good way to put it. Too much concurrency is bad, and I don't know much about what I'm about to say, but is this HVM? Like,
HVM kind of implements something similar to this, yes.
okay. Yeah, because it mentions experimental parallel programming languages, which essentially, yeah, and this makes perfect sense. This is because operations tend to be fine-grained compared to the overhead of scheduling and synchronizing. Like, this must be a pain in the fucking ass, because, like, to do a plus, we are doing all of this overhead.
Yeah, no, this is like this actually um, this is actually something that you hear about a lot when you get into concurrency. Like, yeah, there's overhead. Just because you're using 8 threads, it doesn't mean you can go 8 times faster, even if your problem is perfectly parallelizable, because
No,
of
but
the communication overhead.
yeah, but is that all still true when you're talking about like GPU programming? Like, I know
Uh,
nothing about it. I'm completely clueless.
I don't know that much about GPU programming either, but I think in the context of a GPU, like usually you don't have much communication between threads in that context.
Yeah. Using the shared state model directly. Okay, now we're gonna see an example on how to add the locking system into the things. So we're gonna start by making a queue in declarative form. So that's the concurrent, yeah, that which is this thing. It
Actually,
is
it's a
using
stack.
exchange. Oh, it's a stack. Sorry, the queue is later. My bad. So it's a
Yeah, this one is a
stack.
stack.
We have the push and the pop, which is okay. And it's saying here exchange is atomic. It can be used in concurrent setting. And then you ask yourself, okay, if we have this, what the fuck is the problem? And the answer is nothing. But then there is the explanation. Uh, where is
Yeah,
it?
exchange only works if you only have to deal with one stateful thing at a time, right?
Yeah, exactly. If you have more than one statement, yeah, but that is written. Oh, here it is. The concurrent stack. The concurrent stack is simple because each operation does just a single exchange. Things become more complex when each operation does more than one cell operation. And that's why this may be a problem in the general case, not in this case. Then we go to the simulation of a slow network. Yeah. Then we go to the simulation of a slow network, which is essentially doing the delay. And here's I have my first question because I don't know, maybe I'm misunderstanding something. I'm not understanding this talking passing mechanism because we are creating a cell here. I understand that. And we
Yes.
are returning a procedure that takes a thing. That's also okay. Then we create two unbound variables, and then we do an exchange between. And then I don't remember anymore the order of the arguments, but we are using all the stuff that we created ourselves, not
Yeah,
the arguments.
basically, yeah, no. What exchange does in this case is it's going to bind the previous value of the cell to the old variable,
Okay, so
and
C
then
to
it's
old.
going to, yeah. So old now is bound, is unified with the previous content of the cell, and then new, the variable new becomes the new content, but it remains unbound.
Wait, but what are you doing with new? Why is new in this exchange call?
Because the point is that now the cell has an unbound variable inside of it.
Ah, you're putting this inside C,
Yes.
but the contents of C is in old.
Yeah, the previous content is in old, and the new one is just the new
Is
variable, which is remains unbound.
which is what C is pointing to.
Yes.
Okay. Yeah, but how is this? Well, let's not skip steps because here's the situation. We implemented the simulation of a slow network, but there's a problem. Does not preserve message order. And what is the reason? Because you can have different values of D, which means
Yeah.
that a particular message, because it's in a separate thread, may be received even though it was a second dispatched, it may be received first because the delay is smaller.
Yeah.
That is okay. We want to fix that, but I don't understand how this is fixing that. That's kind of my question.
Okay. Before we do the delay, which is inside of the thread there, you see, we do
Yes.
the exchange, which means
Yes.
that this new cell now has an unbound variable inside of it. And what's the first thing that we do after the delay?
We wait for old,
We wait for old, which may still be unbound at this point, because the previous call didn't finish yet.
which may still be unbound because the previous. How is that's actually my problem. How is the previous call related to any of this? These are all new things. C is new, right?
No, but this returns a procedure, and C is captured by the closure in the procedure. Or rather, the closure that implements this
Ah.
procedure.
Wait, so this is okay. So first, this is using the lexicoscoping trick,
Yes.
and these are instantiated like.
Every time you send a message to this object, which is simulating a slow network, you're generating a fresh old and new variables.
Yeah, but how are you waiting for the previous call one then? That's
Because
kind
you
of my.
see, when you initialize the cell, you initialize it with units, which is determined, right? It's not an unbound variable.
Yes.
But then every time you send a message to this object, which is represented by the procedure that this function returns, the first thing you do is you replace the contents of C with an unbound variable.
Yes.
And then you wait on the previous variable to become bound before actually sending the message to the underlying object.
Ah, okay. So this is kind of like passing the baton, like as it
Yes,
goes.
yes,
This is the
exactly.
yeah, but this is the reason why I understand why data flow variables are cool, but I'm not so used to it, so I still think it's hard to think about it. This is it. Like every time this happened many times. Like, oh, okay, it's because of the data flow thing.
Yeah.
This is not written in here, and I'm a monkey, and I'm a dumb monkey. Like, you have to think hard about it.
Yeah, it took a bit for it to click for me as well because, like, um, when I first saw this exchange primitive, I was like, dude, why do you have exchange and not something lower
No, no, no,
level?
no, no.
Like,
Yes, pause there. I remember that discussion, but you found a second reason why this is done. Like, uh, this book puts in your head that exchange is done like this because it's atomic. But you found another reason in one of your previous comments in the chat many weeks ago, and
it's
it's
because it
related about the
interacts.
read-only variable and things like that.
Yeah, because you can always do this trick where you exchange the contents of the cell with an unbound variable, and you can make it read-only to make it really secure, right?
Hmm.
And then you guarantee that everything will execute in a well-defined order, even though you're doing mutation on the cell.
which is pretty cool. Well, it's not life changing. You can still do that with like mutexes in C or whatever. But this is pretty cool. It just takes two steps when thinking about it to get there. But anyway, so this is how we're gonna solve it, and apparently this is strategy called token passing, which well now makes way more sense to me. There is an explanation here attempting to teach you how that works, but I found this to not be enough. Marinho helped me, and there's also this explanation here, but it doesn't really make sense until it clicks that you're passing the baton further and further and further. Okay, give me a moment. I'm pausing. Okay, there we go. So then there's that, and then yeah, more cool stuff. Programming with atomic actions, and these are the chosen abstractions to do shared stateful concurrency, which are locks, monitors, and transactions. I confess, I never heard of monitors before. Maybe I've seen them before, but not with that term. We're not going to look at them today. We of course seen transactions before, like of course, and locks I like. Pretty okay as well. So locks, where's the thing? Yeah, here you go. Locks is essentially the very like vanilla default approach for concurrent programming. Well,
Yeah,
I
it's the
should say
low. Yeah,
imperative concurrent programming.
yeah, it's the low-level primitive that is used as a foundation for monitors and transactions, right?
Yeah. Well, there is a little bit of discipline, right? It's written somewhere in here. There is a little bit of discipline that you must put like a single access to the critical region in that lock, and that's like on you. Probably there are some very niche and obscure programming languages that actually like mechanically check that, but I don't know any of them. So that's and
Uh,
then we have monitor, which essentially puts like it's very similar to a lock, but instead of exiting, you go to like a waiting point.
yeah, and then you can let someone else do something in the monitor while you wait, basically.
Yeah. And then we have transactions, which is essentially like try to do some stuff. If you successfully did all the stuff, commit your change to the state. And if you failed, you should abort and should not commit any of those changes that you did inside of the transaction. Very cool.
Yep.
So there we go. So then, yeah, then it talks a little bit more about reasoning with atomic actions. You have to prove that the action itself it's okay. Then like a sequence of them is also fine. Nothing groundbreaking again. Then we have recommendations of potentially books we're gonna read in the future. I vote for the concurrent Erlang. I think this is the one that I have.
Wow, it's by Joe. Oh, it's by Joe Armstrong, so it's probably good.
Oh no, it's not. I don't have the concurrent programming in Erlang. I have designing for scalability with Erlang. Well, anyway, so we have concurrent programming in Erlang, concurrent programming in Java, principles and practice, and transaction processing concepts and techniques. Okay, and then finally, wow, this was really fast, 23 minutes. Um, and then we have the locks. And this, like I said, this is the classic imperative programming solution to do concurrency. So you're gonna use, like, you're probably using pthreads already, and then I don't remember if pthreads gives you this. I don't remember. Well, like, you can implement this yourself. Like, this is not that hard. With locking. So how does that look like? That looks like the too much spoily. So let's not go there. You have a critical region, which is essentially well, oh, this is the part that it talks about. So you have internal resources and then external resources that can be, and you want to have control access to these resources. Uh, to do the internal thing, where is it? Yeah. Uh, the resource is inside the program, then the programmer can guarantee that it cannot be referenced outside the critical region using lexicoscoping. So you have well, assuming that you have the more powerful lexicoscoping mechanism. This kind of guarantee can in general not be given for resources outside of the program. So if you're talking about like a port or a socket or a printer, uh, like external devices, this is very hard. Like you cannot. Well, you kind of can, but it's not the full solution for using lexicoscoping. For the resources lock RNA to the programmer, but he must follow the discipline of only referencing the resource inside the critical region. So that's what I said. You must follow some discipline. It doesn't really
Yeah.
matter that you have like a control access managed thing if you are allowing other parts of your program to access that resource. There are many different kinds of locks that provide different kinds of access control. Most of them can implement in Oz language entities you have already seen. So then these are the things. We have new lock, L, which is returns a new lock. Islock X returns true if and only if X references a lock. And then we have the lock, like body or whatever. Um, and there is a caveat that note that these can be called many times with the same lock X. That is, the critical sections don't have to be contiguous. So you can have like locks inside locks.
Yeah, you can call the same lock recursively. This is what it means to
Yeah.
be. This is what the book means when it says it's a reentrant lock that the Oz language provides.
Yeah, we're gonna see the implementation of that.
Yeah, we're gonna see that in a bit.
Yeah, then we have, okay, and then now we're gonna have the queue. So this is the declarative version of the queue. Pretty simple, we've seen this before. This is still the funny queue that kind of non-intuitive. If you delete when the queue is empty, it will delete the next inserted element. And the reason that works is because this is based on the default variables,
Yeah.
which means that when you bind it, which happens when you do an insert, there will be a side effect informing the deletion that hey, I have something in there now, and then delete will delete it. So that's kind of funny. And also there is the size operation, which is not in here, but it also goes positive and negative. This is very weird. Like people would be confused by that. Oh well. Cool. So building stateful concurrent ADTs. So now we're gonna upgrade that original version with new versions. So 8.6 is the declarative normal version. Then we have 8.7 shows the same queue but in a stateful version. And this is using the lexicoscoping trick.
Yeah.
So you have the mutable cell, and you have the procedure for insertion, and then you create those things, you unify them, and then you rewrite it. Um, this sucks though, because what happens if you are in a concurrent setting and like you are in the middle of this and then you hold and you halt and you do something else. So
Yeah, you can lose updates if you just do that naively.
and then we go to 8.8 shows a concurrent version of the stateful queue using a lock to ensure atomicity. So pretty simple, we just add lock blocks to the thing. Then we have 8.9 shows the same version written in object-oriented syntax, and this is very weird. Like, um, what the fuck is this like? Is this telling the runtime that this entire class has locking things?
Yeah, basically it's saying every instance of this class, every object that is a queue has a lock associated with it, and you can use the lock inside of the methods of the queue.
Why? Why is that? What does that matter? Why you need to inform the runtime that? You're already using the lock blocks in here.
Because it needs to create the actual lock object that is going to be associated with the instance.
Oh, this is to call new lock then. This is to
Yeah,
call
basically,
this for you.
basically it tells the class,
Oh.
hey, whenever someone calls new to create a new object of your class, make a lock for me and
Ah,
save that because I'm
okay,
going to use it.
that's why this is here. It's basically like convenience.
Yeah.
Cool. Then we have this is 8.9, right? Yeah. Then we have 8.10, which was another concurrent version using exchange to ensure atomicity, since there is only a single state operation. This version is made possible because of the single thread assignment property of data flow variables. An important detail: the arithmetic operations must be done after the exchange. Okay, they changed this from the new from between the old version and the new version. So on the old version, apparently the y is like hidden in parentheses. But on the new version, there's no parentheses. Just like
It
why?
it just asks why. Okay.
Yeah, and the reason is because well, the question is why we need to do this after the exchange, right? Because we we are essentially telling the right resizing the queue by using ends, but these ends are unbound during the exchange process, and that's not good. So then we need to bind them with their actual versions, and if we do that before,
It's gonna wait forever.
it's gonna wait it forever.
Yeah, because it's going to try
Yeah,
to bind n1 to the result of the addition, which depends on n, which is unbound, and there's no
yeah,
other
yeah, yeah,
thread that has access to n.
yeah, exactly. We can discuss the advantages. Declarative 8.6 is the simplest. We cannot be used as shared resource between independent threads. Makes total sense. No problem there. Both concurrent versions 8.8 and 8.10 are reasonable. Notice that the 8.9 is classified as this is not reasonable. Let's not talk about
Yeah, that's kind of overkill for
it.
this case.
Figure 8's use a lock-in is more general since a lock can be used to make atomic any set of operations. We've seen this before. This version can be written with an object-oriented syntax. A 10 version with exchange is compact, but is less general. It's only possible for operations that manipulate a single data sequence. Okay, then we go to tuple
Couple
spaces, which I
spaces.
I never heard it before, especially with the name Linda. And apparently a tuple space abstraction is sometimes called a coordination model. And a programming language with that is sometimes called a coordination language. Man, these guys love labeling things. I have a question. So apparently this is a multi-set.
Yes,
Why?
because you may want to put the same tuple in there multiple times.
Why?
Because if you don't, that means you are essentially dropping messages if you want to think about it in a message passing way.
Okay. Okay, so what is this? We actually talked about it without saying what it is. So this is essentially a memory region where we're going to be storing tuples in the form of a multi-set. The reason why it's a multi-set is what Marinho described. Pay attention that this is the how do you identify a member in a tuple space is by the label of the tuple, which means that you can have multiple tuples with the same label but with different contents.
Yeah, the book actually mentions here in the next paragraph, this is slight simplification because the usual formulation of Linda you can actually do pattern matching on the
Yeah.
tuples.
Uh, yeah, but I'm just mentioning this because I had this question when I was reading this. Okay, but what if you have tuples with the same label but with different content? So those are considered the same by the lookup. So that's a little bit weird if you think about it. Anyway, so you have these three operations, which is like add something to the tuple space, blocking read. So you're essentially looking for this label, and if it exists, you are removing it and binding it. Read non-block. Okay, and I should mention that all of these are atomic.
Yep.
Read non-block is a synchronous read, which means that we're gonna just proceed. There is a funny hack here. So the book, in order for the book to not use the the choice thingy, is it the choice thingy? Well, I don't remember. The predicate that tells you if a particular dataflow variable is bound or not. In order for the book to not do that and piss off Marinho even more, they introduced a boolean for it. Like this is
Yeah,
100% not necessary if you have the other thing. But okay.
yeah, yeah.
So you are looking for this label in this tuple space. No, uh, no, you are looking for this label in this tuple space, binding to T if it's there, and returning a boolean to tell you if it worked or not.
Yeah, that's
Like they were
we're all
definitely saying there is a baby in America there that will be pissed if we do this. So let's do that.
yeah, like we're all the way up to mutable state. Like, come on, we can use bound use that, can't we?
But the book kind of puts in a way that it's kind of cursed. So they don't want to use choice or is that. Like they don't want to use those things. Okay, then we have an example. So we start our tuple space, which again is just a memory region saving tuples. So you can think of this as like a global variable that I don't know. I guess the closest thing that people understands of this is an arena, maybe.
It's not quite an arena. This is more like
No, but I didn't say it's
um,
the same thing. I said it's the closest.
no, this is like if Kafka had an actually nice user interface, this is what it would look like.
Well, I think it's well. You're talking about the API, the interface. I'm talking more about the concept, right? So you have a region that you're saving things, and you have a very particular way of interacting with it.
I mean, if you think about it, in this simplification where you can't do pattern matching, the the labels of the tuples are like the topic names in Kafka, right?
Yeah, okay, this is a dictionary. That also works. Uh, yeah, but it's mutable, so that's why I wanted to mention the arena. Anyway, it doesn't matter. It's just a place where you put stuff, you retrieve stuff, you write stuff, and you look up things. So that's how that works. So you have our queue using that. There is a slight observation here. You are the operations themselves are atomic, but multiple of them are not. So you could put a lock in there if it matters. That okay, what happens if between this and this we stop and we do something else? So we could do that. Um, you can also use the asynchronous version that doesn't block. That's okay. Um, Implementing a concurrent queue. Yeah, so this is what we just saw, right? Yeah, 811. So then it's explain to us how we're doing things. So you initialize that, and then you insert things into that. Yeah, before returning, you actually insert the empty queue into the tuple space. So the tuple space is essentially working as your critical region, and we are making and okay, you may ask yourself, why do you need this, right? Because this is doing essentially the same thing as the mutable cell with the same lexicoscoping trick as before, and the answer is because read and write are atomic, and the other ones were not.
Yeah, this one doesn't need to do any explicit locking, and the way it works is actually kind of clever because you're basically saying, okay, this particular tuple space will always have exactly one tuple in it, which is the current state of the queue.
Oh, but that is assured because we're not providing access to the programmer about the tuple space. This is hidden in the lexicoscoping.
Yes, lexical
So,
scoping for the win.
well, full-blown powerful lexicoscoping, right? Because if you just say lexicoscoping, people will get mad. Uh, cool. Yeah, and as I said before, and Marinho also repeated, these things are atomic. You may also say that the exchange version is atomic, but the exchange version has the problem of the ends. Yeah, so you would have to put a lock here, I guess.
Uh, well, the problem is, well, you don't need a lock in this case because this is just a single queue, right?
You're right. No, yeah, but what if you have multiple threads doing inserts? Does that matter?
It doesn't because Exchange will always do its operation
Yeah, yeah.
atomically.
It doesn't matter that it's unbound at this point. Yeah, so you don't even need locks in this version. But this is harder to read than this. I'd rather read this. So,
Yeah, double spaces are nice. I wish they were more well known.
I think like in the majority of the cases, the reason this is not popular is because if you're doing like low-level imperative programming, you're gonna use an arena. You're gonna use this. And if you're using a
And
high-level one, you're gonna use a dictionary. Like if you don't have the message passing requirement, like if you're actually not using that for anything at all, like, do you really need this? Can't you
I
just
mean,
use a
it's
dictionary?
I mean, it gives you a nicer primitive than just locks because the problem with locks is that they don't actually compose particularly well. Um,
No,
you have to
sure.
go all the you have to go all the way to transactions to get that property of
Well,
composition is nice.
well, sure, I agree. If you just use a dictionary, you're gonna have to wrap things with locks, potentially. I understand that. But would you like it goes back to the old thing that like it's a bad argument, but people keep using it with like, are you gonna make more people uncomfortable by using a tuple space instead of just using a dictionary with a couple of locks? Like, I'm not saying that's a good argument. I'm just saying that people will you say that I rather use something I know because the extra cost of writing it a little bit more a little bit more letters is not that huge.
Yeah, but
But
that argument, why would you ever learn anything?
exactly, right? So why are we doing anything above assembly then? Why are we doing anything above wires then? Like what are we doing?
Yeah,
Uh,
come on, you should flip your switches by hand
exactly.
to put down the machine codes in your RAM or whatever.
You're gonna employ people. You're gonna increase the economy. Oh man, people would not take that as a joke. Uh, okay, anyway, so then we have the OOP version that I think nobody cares. Well, there is a clever thing about this though, because it's using a queue. Is this the one using a queue? No, it's using a dictionary as the internal implementation of the multiset. So that's cool.
Yeah, it's a dictionary of queues, basically.
Where are we? Yeah, so this is just talking about implementing that. Um,
Oh, now we see the lock
yeah,
definitions.
the lock types. Uh, okay, a bunch of things. Implementing locks. This is what matters. So a simple lock is a procedure. Oh, wait, and we should mention that the built-in locks provided by the system are thread re-entering locks, which you're gonna learn what they are uh, shortly. The simple lock is a procedure that takes zero arguments. Procedure P as arguments in the critical regions. Well, again, this is conventional, which means that we are assuming that P is the only entry point to the critical region. Any thread that attempts to enter the lock while there is still one thread inside will suspend. The lock is called symbol because a thread that is inside the critical region section cannot enter any other critical section protected by the same lock. So this is not re-entrant.
Yes.
It is if it first has to leave the initial critical section, simple locks can be created by the function simple locks. So let's take a look. This one. So this is creating a this is using the token passing mechanism, but like pretty straightforward.
Yeah,
You
this is
are
fairly minimalistic.
waiting for your turn, doing the stuff, communicating to the next guy that you're done.
Yeah, and there's a slight tweak to make it actually not block if the P throws an exception.
Yeah,
But
there is
that's
a
just
problem of
wrap.
like what? Yeah, this is actually kind of funny, right? Because we have to keep adding external like extra patches to our solutions because we have exceptions. There should be like a footnote all the way in chapter 1 or 2 saying we are introducing exceptions, but you're gonna regret that. So then we have the correct simple lock, which now patches the existence of exceptions, which is essentially just putting try catch, but you're using the finally, which always execute. So that's pretty nice. This removes repetition. Um, Cool. Then it's talking about the exception. Then we have the thread reentrant lock, which extends the simple lock to allow the same thread to enter other critical sections protected by the same lock. So if you're doing recursion, that's okay.
Yeah, if you're doing recursion, it just works. It doesn't block you forever
It
while you
doesn't
wait
block you
for
from
yourself.
yourself. Yeah, it is even possible to. That's so funny. I got blocked by who? Myself.
Yeah, it's like you're playing Snake and you run into your own tail and die.
Exactly. Other threads trying to occur in the lock where P is acquired. Um, when lock is released, it's going to do the thread standing first in line. I actually don't know how this is usually solved. Is this like a first in first out in like normie languages as well?
It might be. Depending on the language, there may be a priority system, right?
Yeah, but how is the usual convention for that?
Well, if you don't have a priority system, it would just be first in, first out. That's just the simplest, most minimal
Mm.
semantic that you can give that actually allows you to reason about these things.
Yeah, that makes sense. This assumes each thread has a unique identifier T. Yeah, we're gonna read that. So this is the full version. So a couple of things. Okay, there are a couple of questions. I actually also read the questions. This assumes that each thread has a unique identifier T. It's different from the literal unit, and that is. Oh yeah, this is a like. I'm so glad this is not allowed to because there would be an individual that would make a thread name unit,
I
and that is
think you
obtained
can't
by.
actually.
Go
Yeah,
on.
I'm pretty sure you actually can't choose the identifier of the thread. It is assigned by
Yeah.
the system when the
Yeah,
thread is
yeah. That's
created.
definitely a thumbs up for that. The assignments to cur thread have to be done in exactly the places shown. And then I have two questions to answer. What can go wrong if we swap the wait old, and the current thread this, and swap the assignments of unit, the order of those assignments? So let's take a look. So first, what is going on? This is again token passing mechanism. So lexicoscoping, full-blown lexicoscoping. We have token current thread. Uh, Unit starting as cells of unit. Then we are returning the procedure log. The first thing we do is to check if the thread that is currently executing this procedure is the contents of current thread. Because if it is, that means that we are in a recursion.
Yes, we're already inside of the lock, which means we can just proceed.
This is not going to make sense reading like this because we need to see what the else does to understand why this works. But that is the base case.
Yeah.
Uh, and then we go to the else. So in the else we do the token passing strategy using the exchange and the old and the new and passing the baton. And then and then we have current thread equals thread. So here we are putting ourselves into the seat of like saying this is mine, okay? This is mine. Then we execute P with a try finally because we we don't like ourselves, so we introduced exceptions before. And then on the finally, we actually bind the current thread and the new to unit. Right. So now let's go to the questions. What if you swap wait old with current thread this? I think you're gonna override the priority queue. Well, not the priority queue, but the queue of you are you are not waiting for the old one to be done, and you're already assigning yourself. So you are overriding with your turn.
Yeah, you can end up deadlocking other people because they think they are
The owners.
not in the lock even though they are. Yeah, that would be bad.
Yeah, and then what happens if you swap the current thread equals to unit and the new equals to unit? So if you swap those, you are informing that you are done before removing, like getting out of the seat, so to speak.
Yeah, what can happen is the current thread can get preempted between those two lines, right? So if you do the binding of the current thread afterwards, what can happen is you bind new to unit, then you get preempted. Somebody else acquires the lock and sets the current thread to be themselves. But then you go and set it back to unit afterwards when it's your turn to run again.
Exactly. So in that exchange, somebody got the seat, but you grab the seat back to yourself. So like you're messing things up on the synchronization of the threads. So that's not gonna work well. And I guess that's essentially it. We have still 10 minutes. So next time is gonna be next Sunday. So what are we reading next? Have we talked
Definitely
already about that?
monitors.
Monitors.
Definitely monitors, yeah. Because that's
So,
the
And I
literally the
should
next
maybe read
chapter.
this book.
sorry,
I should
Commander.
maybe read this book because I also need to research the multi-threaded environment at my current job. Then
Well, there
I'm
is a
already
problem
doing
there
that.
because uh, your job is C++, right?
Yes.
There is a potential problem because the concurrency models that this book explores assumes. Anyway, am I right in saying that Oz is more powerful than C++?
Well, it definitely doesn't give you as much lower level control. So in that sense, no.
No, but that's not what we're talking about. We're talking about like capable of expressing different programming models.
Well, in that sense, yes, Oz is it's very well designed to allow you to do multiple paradigms in a very clean way. So like,
Well, mind paradigm is really simple, by the way. Just saying, it's just threads and mutexes for now, mostly. So
Yeah, so you're gonna only be taking advantage of locks essentially.
okay,
well, I kind of want to rewrite a big chunk of it, so maybe more than that. I actually consider using conditional variables and such, but yeah.
Oh, okay, no, if you're going all the way to that extent, just go for it. It's just because a lot
Yeah,
of
yeah.
things in this book are based on the premise that you have something called data flow variables, which I have no knowledge that C++ has.
What is that?
We can talk about
I
that after we finish. Give us 2 minutes.
Can you just type me the name of that?
Data flow
okay.
variable, sure, Marin.
Yeah, yeah.
Okay, so Marin, what are we going to be reading next? So 8.4 is 8 pages. That's very fine. And then 8.5 is 17 pages. So that would be okay. 84, 84, 85. Oh, but then we have but the Java one is just 2 pages. So let's just finish 8. What do you say?
Agreed, agreed.
Okay. So let's finish the recording.